All right, now it's working. Let's go ahead and get started. So first we're going to do a couple announcements. Make sure you sign in. Fire talks are still happening. They'll be in 2 weeks, the last meeting. Please sign up. You don't have to talk for long. It's a really good opportunity to be able to show what you've been working on. You can put it on your resume. If you don't have anything to talk about, then we're just gonna sit here for an hour, and that's gonna be your punishment or something. I don't know. Then we have to come up with something and plan on it. So please, it is a really good opportunity to get out there and practice your public speaking skills while also showing the cool stuff you're working on. Sign up is on that QR code link. I think we also posted it in the Discord. If not, we'll post it in the Discord soon. So, yes, do that.
If you don't sign up, I'm going to talk about combinatorial logic, and nobody wants that.
Besides that, TechSaw CTF is this weekend. SFS students have been working really hard on getting the CTF set up. Right now, I believe there's 29 problems that are ready for you to solve. If you sign up using your UTD email address, then you do qualify for a prize. The top 3 teams will be getting subscriptions to Try Hack Me. And if you've never done a CTF, it's a really good opportunity to try a more entry-level one written by me and a lot of the SFS students that are in this room. Besides that, CSG will be hosting an open lab during the CTF this Saturday from 10 a.m. to 3 p.m. So if you've never tried a CTF, or if you want to participate in a CTF with a group of people, then show up to our lab. It's in ECS 4.619. We'll have some donuts in the morning and just get your hands dirty and figure out how CTFs work. We'll provide some guidance. We're not going to give you solutions, of course, but at the very least, we can kind of guide you if you've never done it before. Last note on the CTF is TechSaw CTF will be occurring from 10 a.m. Saturday to 5 p.m. Sunday, and you can sign up for it. The link is in the announcements for our Discord. So let's go ahead and get into the topic of today. I'm going to be trying to explain a pretty complicated topic that requires a decent amount of background knowledge in a short amount of time. So if you feel lost, first of all, I apologize, and second of all, that's normal, because this is, again, a really complicated topic, but that takes a lot of run-throughs until you start to understand it, but I can at least hope to introduce you to it so that you can start to look at other resources and spend more time and be able to learn how to exploit binaries. One last note on that, if you haven't taken it already and you're interested in delving into this topic for a whole semester, the undergraduate course 4301, Candle, Cyber Attack and Defense Lab, taught by Kanguk Ji, is essentially this, but over a whole semester doing more complicated types of binary exploits. So if you're interested in this, I highly suggest taking it. It's every spring, I think. So, brief overview of the topics we'll be talking about is the intro to exploitation. Then I'm going to give some overview on assembly. Again, assembly would take like a whole semester if you want to properly learn it, at least. So this is just like a reference. And then some architecture concepts that are necessary to understand. Then last, we'll be talking about a specific example of a stack-based buffer overflow where we put it all together in a demo. So, what is system security and binary exploitation? System security is essentially the process of protecting system resources. So you can think of this as protecting any of the operations such as files. It could be protecting the memory while it's running, or the CPU as it's executing commands or instructions. And when you're doing security, there's 3 things you want to keep account of, and that is confidentiality, integrity, and availability, or the CIA triad. Essentially, it's protecting confidentiality is making sure that people don't read data you don't want them to. Integrity is making sure that people don't change data you don't want them to. And last, availability is making sure that your resources are always available to access. So if you like DDoS something, that would be an availability attack. Binary exploitation is a subset of system security where you're abusing poor coding practices in software to be able to access something that you shouldn't. There's many different methods of doing binary exploitation. Some common ones include buffer overflows and string format attacks. So there's a lot of real world impacts to a lot of our hacks that we see in the news are done through binary exploitation. Some well-known examples are the Morris worm. This was a worm in like the 1980s, often known as the first hack or the first worm, that this college kid exploited a buffer overflow and it caused every computer essentially in the network at that time, which I think was during ARPANET or right before ARPANET, causing about 2/3 of the internet to shut down because it kept on replicating itself and using all the system resources once it got onto a machine. And they couldn't figure it out, and every single computer in the world was essentially shut down for a couple of days. So very, very fun example. Another example of this is Heartbleed. Heartbleed is a big attack that happened a couple years ago, where XKCD explained it here, where when you're connecting using, when you're using SSL, which is a method of securing data during connections, you could essentially ask for more data than you should have been able to receive. So you could ask for potato and say, I want 6 letters back, and it would give you potato. You could ask for bird and say that it's 4 letters, and it'd give you bird. Then you could ask for hats, but say that hat is 500 letters, and then it's going to find hat, and then it's going to print out everything after hat in memory at the same time. So essentially, the way that Heartbleed was used was you'd ask for something, and then you could print out all the data that is after that, and if you're lucky, you'd find a password that was hidden in that data, or some other secure information that you shouldn't have access to, allowing you to bypass security measures. A couple other examples. WhatsApp voice over IP. I don't remember what that one was, so I'm not going to talk about it. And the last two are Xbox Homebrew and Twilight Hack. Those were 2 buffer overflows that were used to exploit the systems and gain root access. So the Xbox Homebrew was for the original Xbox, and Twilight Hack was for the Wii. And they allowed anybody to have total control of these game consoles to do their own homebrewing projects or whatever they wanted with it. This is just a small list of different ways that binary exploitation is used. A lot of attacks come from binary exploitation techniques. So let's talk about some of the fundamentals that you need to understand to begin to learn more about this process. So if you've taken, I think it's computer architecture is what it's called, then you'll have some of these fundamentals, but computer architecture here teaches you MIPS. Most machines don't use MIPS unless it's like a PlayStation 1. So some of the concepts will apply, but we're going to be specifically talking about x86 64-bit, and that's pretty much every Intel device. Most laptops, most MacBooks, up until they switched over to their M1 chips, are all going to be using the same assembly instructions. So it's the human. We can think of x86 or assembly as a human-readable form of the zeros and ones that our computer understands. It comes in 2 flavors, where the main difference is just kind of how they organize the instructions. In Intel, I'm not going to even talk about that. Yeah, 2 flavors. Intel is best. AT&T sucks. Get with it. So, with the assembly, there are things called registers. Registers are the smallest piece of memory that the computer can operate on. And they're very close and very fast to the CPU. They are only able to hold the amount of data that the CPU architecture is built in. So for like a 64-bit PC, each register can only hold up to 64 bits of data. So that's 64 zeros and ones that a register can hold. There are a number of registers in 64-bit systems, ranging from RAX, RBX, RBP, and R8 through R15. And these registers typically hold any data necessary for its operations. There's also specific registers, such as the stack pointer, that points to the stack of memory, or the top of the stack of memory while the program is running. There's the instruction pointer, which is going to point to the next line or the next instruction that the instruction is going to run. So every time you execute another line of code, the instruction pointer knows where that is. And then there's the flag register. So every time you make a if statement, a flag register is going to carry zeros and ones, and if a specific one in that register is set, then that means it's a true value, or it's a false value if it's a zero. I think I got that backwards, but they carry bits with specific purposes, such as the carry, parity, adjust, zero, and sign bit. So registers are used to store data. Instructions are used to operate on that data. There's thousands and thousands of registers in x86, so I'm just going to whiz over some of the basic ones that you'll see a lot. Again, this is not comprehensive, so hopefully if you're more interested in x86, look it up, you'll find more information. But the main one you'll see is push and pop. That's how you pull data and place data on the stack. Move is when you want to move data from a location into another location. So it can either be from a register to the stack or to memory, or it can be memory to a register, or it can be a register to a register, or I think those are the only three. You might be able to do memory to memory. I can't remember. And then load effective address is LEA. Call is how you call functions that are predefined in your code. And then return is how you return from functions in predefined code. There's also your basic arithmetic instructions that let you add, multiply, divide, shift left, shift right, XOR, and subtract. And last are the control flow instructions, and these you can think of as your while loops, your for loops. And they're all done through comparisons, testing, and jumps. So if you have a if loop, it's going to compare the value of a register to another value. So say you want to, if x equals 1, then enter this if statement. That's what compare is going to do. It's going to see if x equals 1, and then if x does equal 1, it's going to change one of the flags in the flag register to indicate that it's true. And then jump is going to see that, okay, this is true, so now I'm going to move to this address that is in the argument box. And there's different types of jumps. The basic jump, there's jump less than or equal, jump greater than equal, jump not equal. It's all just different ways of controlling where the program goes next. So that is an entire semester's worth of assembly in about 10 minutes. That's not enough. But I hope that's a starting point, and I will post these slides afterwards so you can use them as reference. Let's talk about some computer architecture basics that are also important to know. We're going to whiz over this one. Most of y'all should know this already. There's different numbering systems. We have base 10, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. You have your binary, that's going to be your zeros and ones, but the really interesting one is hexadecimal. And that's a way of showing binary in a byte form. So we usually use 0x to show hexadecimal, and hexadecimal is by the name, it goes from 0 all the way to F, where F is 15. So it's a 16-digit. There's 16 digits represented by all the symbols, and we use hexadecimal to show different values inside, or different values of memory or of instructions. It's essentially all the zeros and ones, but crunched together. So we can think of a bit as being a 0 and 1. A byte is going to be a single hex digit, or 2 hex digits, 3, 5. So 8 bits is 1 byte, and that's represented by 0x35. And then we have a word, which is 2 bytes. And then we have a double word, which is 32 bytes, and that's what most of our older CPUs use, is 32 bits. And then last, a Q word, which is 8 bytes or 64 bits, and that's what modern CPUs typically run with. Another concept to understand is little versus big Indianness. Has anyone heard of this? All right, good amount. So this is something that you'll be taught in computer architecture if you haven't taken it. Essentially, it's the idea of how do we store data inside a memory. So typically when we think of numbering systems, we have 1, 2, 3, 4, 5, 6, 7, 8. That's our large number, where it's what, 12,000 or 123,400, I don't know, big number. And the number on the left is the biggest number, and the number on the right is the smallest number, where 8 would be 8, and then this 1 would be, I think, 100,000. I'm not good at math. However, that's not very efficient for computers to access in memory. Instead, it's more efficient to access the smaller or the larger number on the right side and the smaller number on the left side. So most Intel systems are going to use little endian to store this number, where they have 1, 2 on the right side, 3, 4, 5, 6, 7, 8. And that's still going to represent this number. It's just a different way of storing it. Now we're getting to some more interesting stuff where we have an understanding of what a computer is. A computer is essentially a way of making operations. It has memory, cache, registers, and it has an input and output and some sort of code to be able to run that output. Now, the program is going to define what the computer does. And we can think of a program as a collection of instructions that performs a task when executed by the computer. And at the lowest level, it's just going to be our bits, but they're going to be organized into machine code or our instructions. In this topic, we're going to be talking about specifically ELF programs. ELF is a method of compiling programs under Linux to be executable. So anytime you use GCC to compile a program or Visual Studio to compile a program, it's turning it into the ELF program file. And that's just how the Linux operating systems understand how to execute that program and provide the information to the CPU. Some other common formats that exist are Mach-O. That's what most Mac systems use for their executable. Then there's PE, which is what most Windows systems use, or EXE file. That's going to be packaged as a PE file. And then a lot of older Windows systems, such as DOS systems, they're going to use COM or MZ. But again, we'll only be talking about ELF today. So when you compile a program so that the computer can run it, there's a lot of really complicated stuff that's going on in the background. You start with your source code, and we can think of this as like C code or C++ code. And it's going to go to the preprocessor. And the preprocessor, what it's going to do is it's going to look at the heading file or your headers, your prototypes for your functions, and it's going to say, okay, I know what these are. I'm going to now place them to where the computer can understand it and put everything into one file. And then your compiler is going to come in and say, okay, now I see all this C code. I'm going to turn that into assembly so that it can run on this specific computer. And it just looks like a bunch of the instructions that we showed earlier. Last, it goes to the assembler, and it's going to turn it all into machine code. And the machine code is going to look like a bunch of zeros and ones or hexadecimal numbers. And that is something that the computer can understand, because every group of 0 and 1s, it says, okay, I see these zeros and ones, I'm going to do this. And that's how the machine is able to run and execute a program. And last, it's going to link. And essentially what that means is if every time you import the standard library, every time you import C strings, or if you import time library, it's going to see that, and it's going to say, I'm going to go find that file, and I'm going to put all the functions that that file has inside of this one program so that whenever it gets called, I'm able to operate and execute that function that we imported. And that's how an executable gets made. The cool thing about this is you can take that C code or that machine code with all those zeros and ones, and you can go backwards up this tree and have a pretty good idea of what the C code looked like when it was originally made. Now, you're not going to be able to see all the comments, you're not going to be able to know the names of the variables, but you are going to be able to see what the program's supposed to do with some work. So that's reverse engineering. We won't go into that as much, but that's understanding how a program is compiled is very important so that you can take a program and reverse engineer it and start to look for the bugs and the vulnerabilities to exploit. Next, we're going to talk about the memory layout of a C program. So when we think of memory, we typically think of it as one giant block or one giant array or one long list where every single thing in memory has a address, and the next place in memory has the address plus 1 or the address plus 2, and so on and so forth, where everything can be indexed from 0 to infinity or a million or whatever. And the way a program organizes this inside of that block of memory is by splitting it up into portions. So the main portions to know about is the text or code part, and this is typically going to be the only executable part of memory, where inside when your C function is compiled, or when your C program is compiled, this is where the instruction pointer is going to point to, or the instruction register is going to point to, and it's going to say, here's the code, here's the instruction I need to run, I ran it, now let's go to the next address in memory, here's the new instruction, I'm going to run it, next address in memory, and it just goes down that line. The other parts are the heap and the stack. So the stack is going to be non-dynamic memory. It's going to be stuff that's allocated in your function. So every time you call a function and you have like x equals 1 defined in that function, it's going to generate the stack and put x equals 1 on the stack so that it's able to place it somewhere in memory and make changes to it in memory as needed. Now, sometimes you don't know how much memory you need or how large that object you created is going to be. And that's what the heap is for. So if you don't know exactly how much memory you're going to allocate while you're writing the program, then you can use functions such as malloc or I think malloc's a big one. I can't remember the other ones. You're going to use something such as malloc, which is going to dynamically add memory as necessary for the program. And that gets stored in the heap, which is another section of memory that anything can be indexed for your program. Last important thing to know about the stack is that it's structured with a last in, first out. So every time you add something to the stack, that has to be removed before you can remove stuff below it. And that's pretty important for understanding how stack frames or function calls work, which is where we'll start to learn more about how buffer overflows work. Every time you call a function, it's going to create a stack frame. And when that happens, the instruction pointer and the base pointer and the function making the call is saved and placed onto the stack. So overall, a stack frame, we'll get in more in depth, but overall a stack frame will look something like this, where you have your main stack frame, has character B, integer A. It's going to save the base pointer, which is the bottom of the stack, and it's going to save the return instruction pointer, which tells the program, hey, I returned from this function, here's where I'm going to go next in the program. That's after where I called the function. So getting more into depth on that, we have this program on the left here, and it's very simple. It has two variables, it calls foo, and then it returns. So we have the two variables on the stack. The stack pointer, or the stack register, is pointing to the top of the stack, and the base pointer is saved here, and the base pointer doesn't matter because it's main right now. But when we call foo, it's going to allocate a new stack frame. It's going to have the new integers and the new floats, or the new variables. It's going to save the base pointer, which is going to essentially point to the bottom of main, or the base of the main stack frame. and then it's going to save the return instruction pointer, which is going to point to the return after main inside the function, so it knows what to execute after it returns. Similar for the bar, once bar gets called, it creates the variables, it saves the base pointer for the previous stack frame, and then it saves the return instruction pointer so it knows where to return to once it's done calling. And then once all these functions return, it's last in first out, so it returns, that stack frame gets deallocated, the base pointer gets converted to the saved base pointer, and the instruction pointer goes to the saved instruction pointer, or the saved RIP. And then again, same process. That's essentially how a program is going to allocate and deallocate a stack, which is really cool when we get into buffer overflows, and we'll almost do that. But last thing I'm going to talk about is calling convention. Calling convention is, you can think of as how arguments get passed every time you call a function inside of a program. So instead of, so at the C level, you see the parameters where you have the function main, and it has these two parameters that you're passing to it. But inside of the assembly, it's going to be using specific registers to pass those values, and they're set up in the specific order where the first parameter is always going to be RDI, the second parameter is always going to be RSI, RDX, RCX, R8, R9 in that order. And then once you run out of those, then it's going to start passing them using the stack. And then when you return from that function, it's going to send the return value into RAX. These things always have to stay the same. But yeah, you can think of that as how like a C program is going to be calling a function. So let's talk about buffer overflows and why the stack frame matters for that. So has anybody, let's not ask that question. So when you allocate a buffer, so we have like a string, it's going to allocate a number of spots inside of the stack for the letters or the characters of that string to be stored. So here we have this 8-byte buffer. You can think of it as a car 8 in C, and it has 8 bytes to store password, PASSWORD. Every letter takes up one byte. Now, what happens if we try to put a variable, or if we try to put a string inside that buffer, and we don't ensure that it only that the input that we're trying to put in there is 8 or less bytes? Well, then we get a buffer overflow, where we're able to write past memory that is allocated for this string. Now, if we go back to the stack call, we see that, well, we only have this 1 byte for this character. So if we are able to overwrite more than 1 byte, then we're going to start to go down the stack and overwrite things that we shouldn't be overwriting, which can cause unexpected behavior. So you can think of the overflow as going past the original buffer. So instead of doing just password, we type in password 12, and we write 10 bytes. This allows us to arbitrarily change code as we want. The impact of this is that we can do function reuse, we can do return to libc attacks, we can do shellcode attacks or ROP attacks, and these are different ways of exploiting a buffer overflow. Specifically, if we look at function reuse attacks, what we can do is we can take this buffer, cari, and then we can overwrite the return instruction pointer to be the address of another function, say a function that opens a shell. Why? So if we do that, we overwrite this instruction pointer to return to another code. What's going to happen when bar returns? Is it going to go back to foo, or is it going to go to another function? Another function, exactly. Which means we can change what the program's supposed to do to something that it's not supposed to do. There's other methods of doing this, and sometimes you don't have that function to reuse, so you have to write your own functions or stuff like that. But this allows you to get around any protections inside of a program just by changing the return address of that stack frame. So let's put it all together. I have a program here that some of you may have solved already. And essentially, it has a vulnerability where I have 64 bytes allocated for a character, but I call it gets. Does anybody know what the problem is with gets?
It doesn't have a limit to the number of things it gets.
Exactly. So gets is a way of taking input in, but it doesn't check to see how much input you're putting in. So I could type as much as I want and overwrite the allocated amount for story, which means that I can pretty much write anything I want into the stack frame, and it's not going to have an issue with that. Even if you go into like the man page, you'll see that, yeah. Never use this function. So if you ever use gets, you're a sucker and a fool, and you should reevaluate how to C code. But some people do. It's still in the program for backwards compatibility, because way back in like the 80s or whatever, people didn't know how to program. They didn't think about this, so gets exists. So essentially, I'm going to show you how we can abuse this function to be able to do what we want with it. It also has this function, can't run this, where if we're able to overwrite it and change the return address to can't run this, well then we're going to run it, just like we're not supposed to. So let's look at that real quick. So here is our my program's hating me. One sec. GDB/20 story. There we go. So this is GDB. It's a way of looking at a program dynamically as it's running. You can think of it as it is a debugger for the terminal. I have a tool added to it called PwnDGB, which makes it all pretty and easier for me to work with. It's a very complicated tool. I could give a talk on it later. I'm not going to go into details about it tonight, but we're going to break at story time, and then we're going to run the program. And we see, let me make it a little smaller. Oops. Let me do this again. I don't know why it's being that small. Okay. Oh, I'm sorry. I wasn't on the right thing. No one told me. What are y'all on? All right, so here we see the instruction that we're running. We can see the stack. We can see the backtrace, which is all the functions before it. And if I do context registers, you can see all the registers and what's in them. So when we run this program, we're going to see right here in a second that we're going to call gets. And when we call gets, we can input, we'll put 8A's. And when we look at the stack, we see that all of our 8A's are located here at RAX, at the address pointed to by RAX. Now, if we look a little bit more at the stack, we can see here's the saved base pointer in our stack frame. And then, as we know, below the base pointer is the instruction pointer, which we talked about. So below the base pointer is going to have our return instruction pointer, which is going to tell us where to go next when this function is done. So all we have to do is we have to write enough A's to where we overwrite this address in the stack, and it's going to cause the program to crash because it won't know where to go next. So let's do that. There's a more efficient way of doing this, but I don't want to do it. All right, so if we look at the stack now, we'll see that it's broken. We'll see that it's all A's. We don't see our return instruction anymore. And if we continue to run it, then the program crashes and it just sees a bunch of A and it's not having a good time, which means that this program is vulnerable to buffer overflow. So let's do something new where we are going to try and set the return address to be a specific address of our choice. So if we look at info functions, we see the address of you can't run this is 0x401166. So the goal is to overwrite the specific return instruction pointer to, instead of having the original address, to have this address. And we're going to use a tool called PwnTools to do this because it's easy and you don't have to do manual stuff. So I wrote a little demo. Again, PwnTools is another topic I could give a full talk on. So we're going to do some math and we can check that if we were to take the difference between this address, where the return instruction pointer is that it? Yeah, that's it. Where the return instruction pointer is, and this address, where the stack starts, we'd see that there's a 72 byte difference between them, which means we need to overwrite 72 bytes before we overwrite the specific address of the return instruction pointer. So what we'll do in our Python program is we're going to create a payload where we have a bunch of bytes, a bunch of A's, 72 exactly, and then we're going to add the address function to it. So let's put the address function in here that we found. I broke it. So here's the address. You can't run this. And put it there. And then we're going to do something called packing. So if we were to just stick this number inside of the stack as it is, it's going to be in the wrong order. Because remember, it's every time it looks for the address, it's going to be stored in Little Endian, which is the reverse of how we have it here. So PwnTools has a tool for us where it's just going to convert that number into a 64-bit Little Endian number for us. That's what P64 does. And then we're going to add it to our payload. So if we print this payload, I can show you what it looks like. So that's what the payload looks like, a bunch of A's, and then here's the address of our number, which is F11 at, then a bunch of zeros. So let's look at how the program is supposed to run for Pony Story. If we were to run it normally, tell me a story about a pony. I don't want another story. That's normal. But when we run the exploit where we input that payload instead, then it is going to hopefully work where we are able to change the direction or the function that it returns to. So that story didn't make much sense, which is what the printf is in the you can't run this function. So we're going to do one more thing where I'm going to show you the solution in action because I don't have the flag file in here, where actually we'll do this first. So if we do Python, so if we run this and we attach this to it for 436 info font or disassemble, what's it called? What was the name of the function called again? Let's find out. Story time, that's right. break story time. So we're going to put a break right after it receives the input, so we can see what the stack looks like after it receives the input, which is plus 25. All right, and then we're going to continue. We're going to give it the input, and then if we look at the stack, we can see there's a bunch of A's that skips all the way from this address to this address, and then we'll see the function, you can't run this on the stack frame, which means we're successfully overriding what we want. If we continue, that story didn't make much sense. Last, I'll show you the demo, which is the same thing, but it's connected to the challenge, which is listed on our CTF website, and it should spit out the flag for us. Enter, and there's our flag. So we were able to successfully change the program to do something that it wasn't originally intended to do, causing a buffer overflow exploit. To conclude, where did all my stuff go? There it is. All right, so to conclude, there are some ways to protect against the attacks that I just showed you. In fact, I had to disable a lot of the standard protections when I was writing this example because modern systems do a pretty good job of preventing basic attacks like what I just did. The main things you see is a stack canary. A stack canary is essentially on the stack after every buffer that is located, there's going to be or after every stack frame, there's going to be a canary, and it's essentially going to check, say, hey, this random value, if that random value changes before we return from this function, then we're just going to quit the program immediately and say that a buffer overflow occurred, something's wrong, and not let them execute any longer. This is a pretty good protection. It would immediately thwart my attack, especially if it's very hard to be able to leak the address or the value of that stack canary and place that in there yourself, unless there's a vulnerability that leaks it. But if you program it right, there's no then it shouldn't be able to be leakable, and you shouldn't be able to find it, because that stack canary value is going to change every single time you call that function and every single time that program runs. Next is no execution. So there's something called shellcode, which say you don't have that function you want to return to, you can put in your own code and you can place it on the stack, and you can return to your code on the stack and have it execute that code while it's reading it. Essentially, this is a very good way of arbitrarily executing whatever code you want, but NX is something where it changes the way that memory is read to where the program will only execute code in specific portions of memory, the text portion, which we talked about earlier. If it sees that it's trying to execute in the range where the stack is or where the heap is, then it's going to say, no, 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 this is not supposed to be executed. I don't know why I'm here. I'm quitting. I'm out. See ya. And it quits. There's two main versions. NX is the one that's supported by the GCC compiler, and then DEP is specific, or I don't know if I said that right. DEP is specifically done on Windows operating systems. They have the same functionality where they see you're trying to execute the stack. It's going to say, no, don't do this. One other thing to protect it is ASLR and Pi. These are essentially going to randomize the addresses of your functions. So in the example earlier, you saw that I was able to find the function of the address of you can't run this and use it reliably. However, in most modern systems, it's going to randomly assign an address to all the values every single time you execute it. So say that address is 4011 the first time you execute it. The next time you run that program, it's going to be something completely different. So even if I look it up the first time, when I try to write my exploit, then whatever function I do find, or whatever address I do find, I can't reliably use it because it's just going to be different the next time I try to run my Python script or my exploit. There are ways to get around all of these protections. Usually there's return-oriented programming, or there's ROP, there's ways to leak what these addresses are and calculate them, and those are more advanced methods that we can, if you have questions about, I can talk about it more. But for the most part, these protections do a pretty good job of stopping most buffer overflows attack. But again, the main thing as a practitioner of security is, if you want to prevent these attacks, you need to use safe code. So you need to make sure that the functions you're using are checking for bounds, or it's checking to make sure that you're not overriding past the bounds of the amount of memory you allocated for a buffer or something. And a lot of programming languages start to do this for you, especially Rust. That's what they're all about, is making sure you're not doing unsafe practices. However, C and C++ are still very common. They're still very, very powerful, and for good reason. You might want to do weird stuff like this. So just having an idea of, hey, the gets function, or hey, I allocated this buffer for 64 bytes, but I'm reading in up to 128 bytes. Understanding those things and how they can potentially cause a exploit to occur are important things as a practitioner. So here's some references I'll post later that go way more into depth. If you want to look more into like these types of CTF challenges, feel free to ask. I can give you some resources later. But that's all I have for tonight. Are there any questions? Cool. I hope that was digestible. It's a lot in a little amount of time. And I thank you all for coming here. Do we have any pizza left? If we have any pizza left, feel free to grab some. Remember, we have our CTF this weekend. We do have some pizza left. Not much. 4 pieces left. We have our CTF this weekend. I hope to see you all there. If you're not able to be there, you can sign up for it online. It's running all weekend. Thank you.